People all around the world use electricity every day. What would happen if all sources of electricity were suddenly turned off? Imagine what it would be like if we could not use electricity for lighting, heating, and cooking. Without electricity, we would not be able to use our phones, computers, tablets, or even our automobiles. The electricity that we rely upon so heavily is the energy resulting from the attraction or repulsion of charged particles. In our last lab, we discussed electrostatics, which is the study of static electricity. In this lab, we will discuss electrodynamics, which is the study of current electricity. Current electricity is the energy produced by electrons moving through a conductor. As always, before beginning any experiment in the laboratory, be sure you are familiar with laboratory safety requirements. For a demonstration of basic lab safety rules, you can watch our video entitled Lab Safety. Electrodynamics is based on three fundamental concepts: electric current, electromotive force, and electrical resistance. Electric current, electromotive force, and electrical resistance are all related to each other, so a change in any one value will affect the other two values. Electric current is the flow of electrons through a conductor. The complete path that electrons follow as they flow through a conductor is called a circuit. Electric current is measured by determining the number of electrons that flow through a conductor in a given period of time. The unit of electric current is the ampere, or amp. Electric current will not flow unless it has a force to push it through a circuit. The energy that provides a force to keep electrons flowing through a circuit is called electromotive force, or EMF. EMF is measured in volts. Anything that restricts the flow of electrons through a circuit is called electrical resistance. Electrical resistance is measured in ohms. Let's look at how electric current can be applied in circuits. For our experiments with electrical circuits, we will use a device known as a breadboard. A breadboard is a thin board used to hold electrical components in place for experiments or projects that involve electrical circuits. You might be asking yourself, why is it called a breadboard? In the early days of electrodynamics, scientists and engineers used wooden boards to mount electrical components for testing and experimenting. Since the wooden boards resembled cutting boards for bread, they became known as breadboards. Today, breadboards are usually made of plastic with a grid of tiny openings called sockets to hold wires or other electrical components in place. Along the left and right side of this breadboard are two columns of sockets. These columns of sockets are called power buses. Each positive power bus has a red positive sign above and below it and a red line alongside it. Each negative power bus has a negative sign above and below it and a blue line alongside it. The positive terminal of a power supply is connected to the positive power bus with a conducting wire. The negative terminal of the power supply is connected to the negative power bus with a conducting wire. All of the sockets of the positive bus are connected inside the breadboard. So, supplying power to one socket supplies power to all the sockets in that bus. Likewise, each socket of the negative bus is connected inside the breadboard. So, supplying power to one socket of that bus supplies power to all the sockets of that bus. The sockets between the power buses are arranged in horizontal rows that are assigned numbers 1 through 63. The sockets are also arranged in columns. There are 5 columns on the left side, which are assigned the letters A through E, and 5 columns on the right side, which are assigned letters F through J. When we need to designate a specific socket, we can do so by giving its row number and column letter. This socket is designated as 5C. Each group of 5 sockets in a row are connected to each other inside the breadboard. So supplying power to one socket in a group supplies power to all the other sockets in that group. If a wire connects socket 5A with the power bus, power is supplied to all 5 sockets in that group. Here is what a simple DC circuit looks like on the breadboard. A convenient way to trace the path of electrons through a circuit is to use a schematic circuit diagram. A schematic circuit diagram is a 2-dimensional graphical representation of the components of a circuit. We will discuss the individual components, such as the electrical source, cathode, anode, switch, conductor, resistor, and LED in more detail as we proceed with the lab. Every circuit begins with an electrical source and a conductor. The electrical source provides the circuit with EMF to keep electrons flowing through the conductor. Electrons flow from the anode through the conductor and back to the cathode of the electrical source. The electrical source for our simple DC circuit is a power module. It fits into the sockets on the power buses of the breadboard. The power module converts the current it receives from a wall outlet into 5 volts of direct current. A simple DC circuit also includes a switch. A switch is any device that can be used to connect or disconnect a conductor in an electric circuit. The switch for our simple DC circuit is on the power module. A lamp on the power module shines when the module is on. A blue wire, called a blue jumper, conducts electrons from the negative power bus to the circuit. The next component of a simple DC circuit is a load. Any electrical device that converts electricity into mechanical energy, heat, or light, and produces resistance within a circuit is a load. A load could be a lamp, a motor, a heating element, or some other kind of appliance. Or it could be an electronic device, such as a resistor or capacitor. In our simple DC circuit, the load consists of 2 components, an LED and a resistor. LED is an acronym for light-emitting diode. A light-emitting diode is a small semiconductor device that emits light when a current is applied. A semiconductor is a substance that will conduct an electric current if it is exposed to light, if its temperature is increased, or if an electric charge is applied to it. A resistor is an electronic device placed in a circuit to prevent too much current from overloading the components of the circuit. An LED cannot handle much current, so a resistor is placed in the circuit to control the amount of current that flows through the device. The resistor in our circuit provides 220 ohms of resistance. From the LED, a red jumper returns electrons to the positive power bus, thus completing the circuit. If we remove the resistor from the circuit and run current straight to the LED, the lamp shines brighter. This is because more current is allowed to flow through the LED. However, the full current could damage the LED, so we will not keep the power on for long. Next, we place the 220 ohm resistor back into the circuit. The LED does not shine as brightly, but it is in less danger of overloading. Now, see what happens to the same LED with a 10,000 ohm resistor. With this amount of resistance, the LED hardly shines. Earlier in this lab, we mentioned that EMF is measured in volts. EMF is not easy to measure directly, but we can determine the EMF by finding the voltage drop of the circuit. To explain voltage drop, we need to take a close look at a circuit. The electrons in a conductor are usually not spread out evenly. Some regions of the conductor may contain more electrons than other regions. A region with more electrons is said to have a higher electric potential. A region with fewer electrons has a lower electric potential. If one end of the conductor is connected to the opposite end to form a circuit, the difference in electric potential between two regions can be measured. The difference in electric potential between 2 points in a circuit is called voltage. However, voltage can also be defined another way. In a circuit, electrons have more freedom to move around. As a result, some electrons from a region of higher electric potential move toward a region with lower electric potential until all the regions have about the same number of electrons. In this way, the electrical charges become balanced. Moving an electron from one place to another in a circuit requires energy. This energy is also called voltage. So voltage can also be defined as the energy required to move an electrical charge from one point to another within a circuit. Electrons move from a region of higher electric potential to a region of lower electric potential, but they stop moving as soon as the charges balance. To keep electrons flowing through a circuit, additional force is needed. The energy that supplies the force to keep electrons flowing through a circuit is EMF. A battery or some other electrical source connected to the circuit provides the EMF to keep electrons flowing through the circuit. When a load is connected to a circuit, the electric potential will be higher where the current enters the load and lower where the current leaves the load. The difference, or drop in electric potential between the two electrodes of a load, is called a voltage drop. In a simple DC circuit, the voltage drop between the two electrodes of the load will be the same as the voltage drop of the power supply. This value, measured in volts, is the same as the EMF being applied to the circuit. We can find the voltage drop with a multimeter, which is a device used to measure the voltage, current, or resistance of an electrical circuit. The load of this circuit consists of a resistor and an LED. By placing the black probe of the multimeter where the current enters the resistor and the red probe where current leaves the LED, we can measure the voltage drop. We see that the voltage drop across the load is 5.024 volts, which we round to 5.0 volts. In our simple DC circuit, the LED and resistor together make up one load. But circuits often include multiple loads. When multiple loads are connected in a circuit, they are connected in either a series circuit or a parallel circuit. In a series circuit, current passes through multiple loads connected in a single path. The same current flows through each load, but the voltage drop across each load is different. The current must flow through each component of the circuit before it completes the circuit. If one component stops functioning, the current stops flowing, and all the components in the circuit stop working. A series DC circuit with 2 LEDs and 2 resistors can be set up like this on a breadboard. Current flows in a single path through both loads. In a series circuit, the voltage drop across one load will not be the same as the voltage drop across another load. Let's determine the voltage drop across the first load, which is LED 1, and its resistor. The voltage drop is 2.203 volts, which we round to 2.2 volts. Next, we determine the voltage drop across the second load, which is LED2 and its resistor. The voltage drop for the second load is 2.823 volts, which we round to 2.8 volts. From this, we see that the voltage drop across the first load is different from the voltage drop across the second load, which is consistent with the definition of a series circuit. Next, we need to find the resistance of each load. To do that, we must turn off the power. Each component of the circuit has some resistance, but we need only to be concerned with the resistors. We use the multimeter to test the resistance of the first resistor. It has a resistance of 218.3 ohms, which we round to 220 ohms. Now we test the resistance of the second resistor. The resistance of the second resistor is 100.3 ohms, which we round to 100 ohms. We have determined the voltage drop and the resistance of each load. Now, we need to measure the current flowing through each load. In order to measure the current flowing through a load, we must bypass the circuit so that current flows through the multimeter and then back into the circuit. To do that in our series circuit, we first turn on the power, then we unplug the yellow jumper wire between the two loads. When we do that, the circuit is interrupted and the LEDs turn off. Since this is a series circuit, interrupting the circuit at any point disconnects both loads. Next, we plug in a green jumper wire where the yellow jumper wire was plugged in. The extra jumper wire makes it easier to connect the multimeter. For this test, we have replaced the probe tips of the multimeter with these clips. Now we attach the exposed end of the green jumper wire to the clip connected to the red lead of the multimeter. Then, we attach the exposed end of the yellow jumper wire to the clip connected to the black lead of the multimeter. When we connected the black lead, the circuit was closed again, so both LEDs are back on. The multimeter shows us that the current flowing through the first load is 0.001 amperes. To measure the current through the second load, we replace the yellow jumper wire and then unplug the red jumper wire in socket 61F. Then we plug a green jumper wire into the socket, where the red jumper wire was plugged. Notice that both LEDs are turned off. When the exposed ends of the jumper wires were connected to the leads of the multimeter, the circuit was closed again, so both LEDs are back on. We see that the current flowing through the second load is 0.001 amperes, which is the same as the current flowing through the first load. In this experiment, we saw that the voltage drop was different across each load, but that the current was the same. This is consistent with the definition of a series circuit. We have shown how current, voltage, and resistance are affected in a series circuit. Now, let's look at a parallel circuit. In a parallel circuit, current passes through multiple loads on two or more connected branches. The voltage drop is the same for each load, but the current flowing through each load is different. In a parallel circuit, current flows through separate branches, one for each load. Electrons leave the anode of the power source and then follow two separate paths. One path goes through the first load and then back to the cathode of the power source. The other path goes through the second load and then back to the cathode. If one component fails in a parallel circuit, electrons stop flowing through that branch, but they can still follow the second path and still complete a circuit. So the components on the second branch continue to operate. A parallel DC circuit with 2 LEDs and 2 resistors can be set up like this on a breadboard. Current flows through 2 separate branches to complete the circuit. Let's check the voltage drop across the first load. The voltage drop is 5.003 volts, which we round to 5.0 volts. When we check the voltage drop across the second load, we see that it is 5.018 volts, which also rounds to 5.0 volts. Even though the voltages are slightly different, the difference is negligible, so we can still say that the voltage drop is the same for each load. With the power off, we will check the resistance of each load like we did with the series circuit. The resistance of the first resistor is 218.0 ohms, which rounds to 220 ohms. The resistance of the second resistor is 99.7 ohms, which rounds to 100 ohms. We have determined the voltage drop and resistance across each load. Now we need to measure the current flowing through each branch of the circuit. First, we unplug the yellow jumper wire at the end of the first branch and plug in a green jumper wire where the yellow jumper wire was plugged in. Notice that the red LED turned off as soon as we interrupted that branch of the circuit. However, since this is a parallel circuit, interrupting the circuit at this point disconnected only the first load, so the blue LED remained on. Now we attach the exposed end of the yellow jumper wire to the clip connected to the black lead of the multimeter. Then, we attach the exposed end of the green jumper wire to the clip connected to the red lead of the multimeter. When we connected the red lead, the circuit was closed again, so both LEDs are back on. The multimeter shows us that the current flowing through the first load is 0.005 amperes. After replacing the yellow jumper wire, we can measure the current through the second load. We unplug the yellow jumper wire at the end of the second branch and plug in a green jumper wire where the yellow jumper wire was plugged in. Notice that the blue LED turned off as soon as we interrupted that branch of the circuit, but the red LED stayed on. Now we attach the exposed end of the yellow jumper wire to the clip connected to the black lead of the multimeter. Then, we attach the exposed end of the green jumper wire to the clip connected to the red lead of the multimeter. When we connected the red lead, the circuit was closed again, so both LEDs are back on. We see that the current flowing through the second load is 0.016 amperes. The voltage drop was the same across each load, but the current flowing through each load was different. This is consistent with what we know about parallel circuits. A series circuit is easier to set up, but if any component in the circuit fails, the whole circuit shuts down. A parallel circuit is a little more complicated to set up, but if one component fails, the rest of the circuit continues to function. However, since the resistance is higher in a series circuit, it does not overload as easily as a parallel circuit. Because of this, safeguards are put in place to avoid overloading parallel circuits. With their advantages and disadvantages, both types of circuits are used in homes and businesses. In this lab, we investigated some of the properties of electrodynamics. In our next lab, we will examine optics and mirrors. At this time, proceed with the corresponding activities.